In this video, we are going to revisit that problem that we looked at in the last video. In the last video, we found n hat as a function of t, and we found t hat as a function of t, and we found a sub t and a sub n as functions of t. Now that's all great and very efficient, especially if we want the unit tangent and the unit normal, and the tangential component of acceleration and the normal component of acceleration for multiple values of t. Now, if we're just interested in all of those things at a particular t value, like t naught equals 1, there's a much simpler way to do it that involves a little bit less algebra because you're going to be working with numbers instead of functions of t. So I wanted to show you the same problem, but this time instead of finding all of those as functions of t, we want to find them at t equals 1. So the first thing we want to do is calculate the velocity, which is just the derivative of position. So we still have 1, 2t, and 1/3 t cubed. Its derivative is 1/3 times 3 is 1 times t squared. And then we need the acceleration vector. So that's 0, 2, and 2t for its components. Now that's in general. If I want the velocity at time t equals 1, I just plug in 1 for t and I get 1, 2, 1. And if I want the acceleration at time t equals 1, I get 0, 2, 2 for my components. Now if I want to find t hat of t, I would take this vector and I would divide by its magnitude. But if I want t hat at 1, I'm just going to take the velocity at 1 and divide by the speed at 1. Or alternatively, you can think of that as r prime, so that's the tangent vector, and you want to divide by the length of r prime. But the length of r prime and the velocity, or the length of r prime and the speed are the same thing, and r prime and the velocity are the same thing. So it's just two different ways of saying the same thing. It's really depending on how you want to look at it. Are you thinking about geometry, or are you thinking about motion? So I'm taking this velocity and I'm dividing by speed. So my velocity is this vector. The speed comes from taking the components, squaring them, adding them, and taking the square root. So that's 4 plus 1 plus 1 is 6. And I'm not going to rationalize. So that's t hat at 1. Now, if you want a sub t at little t equals 1, that's just the dot product of the acceleration at 1 with the unit tangent at 1. So we're using the same formula as before, we're just using the particular acceleration and unit tangent that we have when t equals 1. My acceleration is the vector with components 0, 2, 2. My unit tangent is the vector with these components. So I'm going to get 0 times that is 0, 2 times that fraction is 4 over the square root of 6, and 2 times that fraction is 2 over the square root of 6. So it looks like I get 6 over root 6. Because it's going to simplify so nicely, I'm going to rationalize. I get 6 root 6 over 6. So the tangential component of acceleration at that point is square root of 6. Okay. Now, if I want to find the normal component of acceleration, remember, our triangle looks like this. Here's a sub t times t hat, and there's a sub n times n hat. The length of this side is given by the magnitude of this number. If this number is positive, it's just that number. If the number is negative, we're going to take the absolute value. But t hat has a length of 1. It's a unit vector, so it's not changing the length at all. So if this is 5 times t hat, this side is 5 units long. Since I know what the acceleration is, and I know what a sub t is, and I know I've got a right triangle here, I can use the Pythagorean theorem to find the third side of the triangle. So we're going to take the square root of the magnitude of the acceleration squared, and we're going to subtract a sub t squared. It doesn't look like we calculated the magnitude of the acceleration yet, so let's do that. acceleration is the vector with components 0, 2, 2, at least at t equals 1 it is. All of these should be evaluated at t equals 1. So I want to take those components, square them, add them, and take the square root. So I've got 4 plus 4 is 8, square root of 8 is 2 root 2. But then we're going to square it anyway. Square root of 8 squared is just 8. So we get 8 right there. And we're subtracting a sub t, the tangential component of acceleration, that's this side of the triangle, squared. So I'm taking square root of 6 and I'm squaring it. So I get 6 there, 8 minus 6 is 2, so a sub n is 2. So what does this tell us? Well, it tells us that our acceleration vector is square root of 6 times t hat plus square root of 2 times n hat. So it looks like we're going like this along our curve. There's n hat in the direction we're turning, t hat in the direction that we're going. And part of the acceleration is in the direction of t hat. So it's saying, take that unit vector and multiply it by square root of 6. This is not to scale. That is a sub t times t hat. And then we're going to take this unit normal vector and we're going to multiply it by square root of 2. That's how much our acceleration is pulling us in the normal direction. So this is square root of 2 times n hat, and this is square root of 6 times t hat. And when you add those together, you get the acceleration vector. So we're speeding up and we're turning. And this is how much. That's the vector that's pulling us in the direction that we're turning, and this is the vector that is changing our speed. Or that's the part of the acceleration that's changing our speed, that's causing us to speed up in this direction. Okay, so that's how we interpret that. Now, what else did we want to find? I've got t hat at 1. Now I want to find n hat at 1. Well, using this triangle, I can solve for n hat. This plus this equals that. So if I want to get n hat by itself, I've got n hat is this vector minus this vector, so I'm just subtracting it from both sides, and then I'm dividing by a sub n. Now that's in general, so of course that implies that at t equals 1, we're just going to take the acceleration at 1, subtract the tangential component of acceleration multiplied by t hat, both of them evaluated at little t equals 1, so maybe after 1 second. This is our normal vector. And we want to divide by a sub n at 1. A of 1 was the vector with components 0, 2, 2. A sub t at 1 was square root of 6, so we just sub that in. T hat at 1 was this. So when we distribute, all those square roots of 6 reduce, and then we're going to take all of that and we're going to divide by a sub n at 1, which turned out to be square root of 2. So I've got 0 minus 1 is negative 1, 2 minus 2 is 0, and 2 minus 1 is 1. We're going to take all of that and divide by square root of 2. That is the normal component of acceleration at time t equals 1. That is the direction that we're turning in. Oh, I'm sorry, I got off the screen. That's exactly the direction we're turning in. And then that is the direction that we were going. Now if I want to find the binormal vector, so there's a plane that contains this unit normal and this unit tangent. So t hat's this way, n hat is this way. It creates a plane. And t hat cross n hat, that's coming out of the page at us by the right-hand rule. The binormal vector points right at you, like this. If I want to find the binormal, I just take this vector and I cross it with this vector. So the binormal at t equals 1 is just t hat at 1 crossed with n hat at 1. T hat at 1 has these components. N hat at 1 had these components down here, provided I didn't make any errors. Hopefully I didn't. Alright, now we just take a cross product. So cross out this row and this column, and then you've got this 2 by 2 determinant. So you do this times this. So we get 2 over square root of 12 minus 0. That gets multiplied by I hat. Then we subtract, cross out this row and this column. This times this, that's 1 over square root of 12, minus this times this, that's minus and negatives, that's plus 1 over square root of 12. And then we're going to add, cross out this row and this column, this times this, which is 0, minus that times that. Subtracting a negative is adding, times k hat. So we get 2 over root 12, and let's do a little scratch work. Root 12 is root 4 times root 3. Square root of 4 is 2. Square root of 3 I can't do anything with, so I just leave it as square root of 3. So this is 2 over root 3. This is 2 over square root of 12, which is 2 over root 3. And this last one is 2 over square root of 12, which is 2 root 3. And all those 2's reduce. And I get this binormal vector. Alright, so there's some plane, and this is just a cartoon. It has a unit tangent in it and a unit normal in it, and they meet at a 90-degree angle. And that unit tangent is given by this vector. And the unit normal points in the direction that we're turning. It's given by this vector. Notice if I take their dot product, I get negative 1 over square root of 12 plus 0 plus positive 1 over square root of 12. The dot product between those two is 0, and it should be because they're supposed to meet at a 90-degree angle. And you should check the magnitude of both of these is 1. So we've got unit vectors that are perpendicular to each other, and one of them is pointing in the direction that we're turning. So we must be turning this way, and one of them is pointing in the direction that we're going. So we must be traveling along the curve in that direction. Now the binormal vector is perpendicular to both of those, and it's given by the direction, well, we can find the direction using the right-hand rule. T crossed with n using the right-hand rule, that's going to point up. The binormal is this. Now you should check. This should be perpendicular to that. So if you take the dot product, this times this is negative 1 over square root of 12 plus 0 plus positive 1 over square root of 12. They cancel and we get 0. Now let's do this one. I get 1 over square root of 18 plus 2 over square root of 18. So that's 3 over square root of 18. Ooh, plus 1 over square root of 18? I don't know if that's right. It's 4 over root 18. Uh-oh, I must have done something wrong. Oh, I see what it is. I missed a sign there. Yep, that's why we check our work, because sometimes we miss signs and then we're wrong. Okay, is that going to work now? Ah, yes it is. So I get 1 over square root of 18 minus 2 over square root of 18 plus 1 over square root of 18 is 0, so that's good. Now my binormal and my unit tangent are perpendicular to each other. And these guys are perpendicular, and these guys are perpendicular. So we've got this moving frame of reference that goes with us everywhere we go. T hat's pointing in the direction we're moving, N hat is pointing in the direction we're turning, and B hat is perpendicular to the plane that contains that acceleration vector. The acceleration vector is saying, let's go that way. Accelerate in the unit tangent direction, in the direction of motion, and turn the whole time. And when you do, the vector that's perpendicular to that plane is the binormal. See, that wasn't too bad. I don't know how long we worked on that example in the other video. It was long. It was still more efficient than using the formal definition of n hat of t to find n hat of t. But look how efficient this was. When I'm given that t equals 1, t naught equals 1, it's very easy to find the velocity at 1, acceleration at 1, t hat at 1, and then we're just doing arithmetic. We're working with a lot of components of vectors that are just numbers, and taking dot products, adding and subtracting vectors. It's not too difficult at all. There's not really a lot of calculus here, just a lot of vector arithmetic. And it gives us a lot of meaningful information, telling us again the direction that we're going, the direction that we're turning, and the vector that's perpendicular to the plane containing our acceleration.